Last time we studied one ports that are part of circuits that are in sinusoidal steady state, and for such one ports we made the discovery that the effective value of the current passing through that one port squared times the real part of the impedance of that one port. We're assuming that one port doesn't contain any independent sources inside, so that it can be represented by an impedance. So that product, the effective value of the current squared times the real part of the impedance, we saw equal to the average power consumed by that, or average power associated to that one port. Okay. In this hour, we will provide a physical interpretation for the imaginary part of the impedance being multiplied by the square of the effective value of the current passing through the one port. And based on that interpretation, we will be motivated to classify one ports, passive one ports, as resistive, capacitive, and inductive. The analysis is quite, which will eventually lead us to the physical interpretation, is quite elegant and uses Tellegen's theorem. So let's therefore consider the following case. Let the one port circuit below consist of LTI passive resistors, capacitors, and inductors only. Okay. Inductors and capacitors only. This analysis can be generalized further to the case where we also have some ideal transformers inside, but for the sake of simplicity, assume that these are the only types of components we have inside our one port, namely LTI resistor, LTI inductor, and LTI capacitor. Furthermore, we're supposing that that one port is part of a larger circuit, and that circuit is in sinusoidal steady state. Okay, suppose it is in sinusoidal steady state. Okay, so this is how we represent our one port N. The voltage across its terminals is denoted by V0T, and the current that it extracts is denoted by I0 of T. Now, since we're in sinusoidal steady state, the voltage and current are sinusoidal, oscillating at the same frequency omega. Okay, Vm cosine omega t plus phi v. Okay, and the current is another sinusoid at the same frequency. This is the magnitude cosine omega t plus phi I, and these are the phases respectively of voltage and current. This yields the following phasor representation. We can write V0, capital V0, which is the phasor of this voltage, equals the magnitude, and then it has the following phase, okay, phi v. Likewise, the phasor of the current is Im, the magnitude, and we have e to the j phi I. Excuse me. So let's recall what we have obtained in the previous lecture for a resistor, LTI resistor, that's part of a circuit in sinusoidal steady state. Okay, IRT equals IRN. Okay, the notation gets a little bit thick here. This M is the M of the magnitude, okay, and then this R is the R of the resistor. times cosine omega t, and it will have some phase, which we denote by phi r. For this component, for LTI resistor, the average power was equal to the effective value of the current squared times the resistance R, or in terms of the magnitude, it was 1/2 times R times the magnitude squared. Okay, remember that for such a sinusoidal signal, effective value is magnitude divided by square root of 2. And for inductor, we had ILT equals IL magnitude cosine omega t plus phi L. We computed the average stored energy in this component, which was 1/2 times the inductance times the square of the effective value of the current. Okay, or in terms of the magnitude of the current, it was 1/4 L and IL magnitude square. As for the average power, both for inductor and capacitor, it was 0, and that we interpreted it as at certain times the inductor stores energy, takes energy from the circuit, and some other times it gives back the energy that is stored earlier, and then those two giving and taking balances itself out perfectly, which produces 0 average power for the inductor, and same holds for capacitor. Okay, and finally for the capacitor, okay, we have capacitance C plus minus VC of t, that's the voltage, which is VC magnitude cosine omega t plus some phase. Okay, for this component, the average stored energy was the dual of this identity, 1/4 C times the magnitude of the voltage square, or in terms of the effective value of the voltage, 1/2 times C times the effective value of the voltage squared. 1/4 C VCM square. Okay, and for the power, the average power for capacitor, like its dual counterpart, was 0. Okay. Now, our one port here will contain arbitrarily many resistors, inductors, and capacitors. That motivates us to define the following numbers. Okay. What we're going to do is we're going to consider all the resistors, and we go resistor by resistor. From each resistor, we're going to pick or collect its average power, and then sum those average powers, and we're going to define that as the total of average powers. And then we're going to do the same thing for the stored energies for inductors and capacitors. Later on, those numbers, those sums, will appear in a very nice way when we try to look at things from the impedance point of view, impedance of our one port. Okay, so here is our straightforward definitions. P average, okay, associated to the one port that we're now studying, is defined as the sum of average powers consumed by or delivered to the resistors in our one-port circuit, which we denoted by N. In other words, P average equals this summation 1/2 2RKIRKM square. And K, the summation, is performed over the resistors. K over resistors. Which resistors? The resistors inside our one-port circuit N. Okay? So once again, P average is you go resistor by resistor, and for each resistor you take its average power and you sum all those average powers and you define this number here, which is the average power in a sense associated to the one port. Then we do the same thing for the stored energies, but this time we just do not collect all the stored energies, but we first collect the stored energies for inductor and also then collect stored energies for the capacitors. Okay, so we define two separate stored energies. The first is E average with superscript L. So this is the sum of average stored energies in the inductors within our one port. Okay, that is E average L equals the summation, where the summation is performed over only the inductors, K over inductors 1/4 LK, and then we have ILKM. So this means the magnitude of the current passing through the kth inductor, which is in our one port N square. And we're gonna introduce a dual definition, that is the average energy, sum of energies, average energies throughout the capacitors. E average superscript C is the sum of average stored energies in the capacitors in our one port. Okay, in other words, E average superscript C equals this sum, where summation is performed over the capacitors only. Okay, 1/4 CK times VCKM square. So this is the voltage, or the magnitude of the voltage of the kth capacitor, and then we're squaring it. And by our passivity assumption, all capacitances, all inductances, and all resistances are positive, so that implies P average cannot be negative, E average L cannot be negative, likewise E average C has to be non-negative too. Okay. And now, suppose we have n components, okay, n components within our one port. Suppose there are n elements in our one port. Okay. Now, voltage, so that means n voltages and n currents. We also have the voltage and current at the port terminals, which we denoted by V0 and I0. So that makes n plus 1 voltages and n plus 1 currents. So the voltage phasors are denoted by V0. So V0 is the phasor of the input terminal voltage, and then we have the other voltages V1, V2 up to Vn. Okay, this is the voltage of some resistor, let's say. The second is the voltage of some inductor within one port, and so on. And the same goes for the currents. Current phasors. Again, I0 is the current at the port terminal, and then we have I1, I2 up to In, and these are the others are the currents corresponding to the elements inside N, namely resistors, capacitors, and inductors. Now we know that the phasors of voltages satisfy KVL, and the dual statement holds true for the currents, namely the currents satisfy KCL. And then we have the Tellegen's theorem. Because KCL, KVL holds in phasor domain, we have the Tellegen's theorem holding also for the phasors of voltages and currents. Okay. In particular, we can write the following. By Tellegen's theorem, okay, it's not directly Tellegen's theorem, but it's implied by Tellegen's theorem, and that implication is quite straightforward to show. We have minus V0 I0 star, and star means the complex conjugate of the start variable. Okay, if I0 is 3 plus J4, then I0 star is 3 minus J4, and so on. Plus the summation K equals 1 to N Vk Ik star, and that must equal 0 by Tellegen's theorem. Okay, this is 1. Here Ik star is the conjugate of Ik. Okay, so that's our notation. Okay, so here is a nice opportunity for me to present an exercise. Why is equation 1 true? Okay. So it would be nice, and it's very short, the proof is very short, it would be nice to prove that this equation indeed is correct. Okay. Now, under equation 1, we will be able to proceed as follows. Now, we write the sum K equals 1 to N Vk Ik conjugate equals, now here we are summing this product for all components within our one port. Okay, because we have n components, and now we're going to write this summation as sum of 3 separate summations, where in the first summation we do the sum over resistors, in the second summation we do the sum over inductors, and for the third summation we do the sum over capacitors. In other words, this we can write as summation over resistors, okay, plus summation over inductors, and finally plus summation over capacitors. What's being summed? What's being summed is this product Vk Ik star. Now we have Vrk IRK star, VLK ILK star, and this is VCK ICK star. Okay, so this is the kth the voltage of the kth resistor and the current of the kth resistor's conjugate, and so on. Okay, so this is our equation 2. And finally, let's express voltages in terms of currents, or for the capacitor, current in terms of the voltage, which we can do easily. In other words, we have VRK equals RK, so this is the resistance of the kth resistor, times IRK. Okay, voltage equals resistance times the current phasor. As for the inductors, voltage equals the impedance times the current, and the impedance for an inductor is J omega L. So VLK equals J omega LK, then we have ILK. And as for the capacitor, we're going to write the dual identity. Current equals the admittance times the voltage. J omega C times VCK. And this is our third set of equations. Okay, now let's combine Tellegen's theorem and the following two equations, 2 and 3. Okay, combining 1, 2, and 3, we can write V0 I0 conjugate equals, so we take this guy and put it to the other side, and that equals this sum from 1 to n, which can be written as sum of 3 summations, and in each summation we can write the following: summation RK. Okay, now if you replace this VRK by RK IRK, what you have is RK times IRK conjugate. Okay, a complex number times its conjugate gives us the magnitude square. Therefore, the first summation produces IRK magnitude square multiplied by the resistance of the kth resistor, plus, now let's look at the summation over inductors. We replace VLK by J omega LK ILK. Again, we have the current being multiplied by its complex conjugate, hence that produces J omega LK and then ILK magnitude square. And finally, we replace this ICK star by this expression ICK. So if this is ICK, ICK star is you have conjugate here, conjugation here, and you have to conjugate J, which is minus J. Okay, so you replace this star with that expression, and what you have is minus summation J omega CK and then VCK magnitude square. Okay, that equals what? That equals 2 times P average. Remember that P average was defined as the sum of all average powers in our resistors. Since the average power was 1/2 times resistance times the magnitude square, this is 2 times the P average. What else? Plus J for omega. Okay. Now, 1/4 LK times the magnitude square of the current is the stored energy, average stored energy. And then we multiply by 4 and divide by 1/4, and then that 1/4 produces the average stored energies in inductors, and then that's summed over all inductors, so that produces our E average superscript L. Okay, so we can write here J4 omega E average superscript L, and likewise that produces 4 times E average superscript C, E average superscript C, and we have therefore this product V0 I0 conjugate equals this. So the real part has some physical interpretation. The imaginary part also has a physical interpretation. So let's get rid of this factor of 2. This is equation 4. Okay. So let Z equals the ratio of V0 to I0. In other words, that's the impedance of our one port N. Impedance of N. And let's give this difference a name. E average delta, defined as E average L minus E average C. Okay? So difference between the stored energies in the inductors and the stored energies in the capacitors. Then the last equation that we obtained, equation 4, implies Z times I0 magnitude square. Okay. Now V0 is Z times I0, so therefore this is Z times I0 conjugate. I0 conjugate will produce magnitude square, and we have for the left hand side Z times I0 square, and that equals 2p average plus J4 omega E average delta. Okay, the difference of stored energies. And let's get rid of this. So this is 2 and this is Z. Let's get rid of that 2. Okay, which we can by dividing both sides with 2. And then what we have here is I0 magnitude square over 2. And that's I0 magnitude divided by square root of 2 and then squared. And that I0 magnitude divided by square root of 2 is the effective value of the current. Hence, we can express this as Z times I0 RMS, or I0 effective squared, equals P average plus J2 omega E average delta. Okay. And this is the equation which allows us see the physical meaning of the real and the imaginary parts of the impedance multiplied by the square of the effective value of the current. Okay, so let's write that down, which is now more or less obvious. Now, this is our key equation of this lecture, star. Star implies that I0 effective square times the real part of the impedance Z equals P average. Okay, this we already obtained in our previous lecture. But as for the imaginary part, we have something new. I0 effective square times the imaginary part of the impedance representing our one port has this following physical meaning. It's proportional to the difference between the stored energies throughout the entire set of inductors and entire set of capacitors. And the ratio is depending on the frequency, 2 omega. Okay, Okay, E average delta. Okay, so this was we're familiar with already from previous lecture, but this thing is new. Okay, so this is new. Okay, and let's put a remark here at this point. Note that P average is the sum of average powers throughout our resistors, and by assumption all the resistors were passive. Therefore, this thing cannot be negative. Okay, so P average is never negative. However, E average delta, this difference may have any sign. Okay, and now if that sign is positive, it means that this energy is larger than the energy stored in the capacitor. So therefore, in a sense, inductors are dominating the capacitors in our one port. If, however, this has negative sign, that means the stored energies in the average stored energies in the capacitors are larger than the average stored energies in the inductors. So that means, in a sense, the capacitors are dominating, or the capacitive effects are dominating the behavior of our one port. And that observation motivates us to introduce the following definition. Okay. Given an LTI passive one port in sinusoidal steady state, and suppose our one port does not contain any independent sources inside, so that it has an impedance representation. Okay, and this is the impedance seen from the input terminals, with real part R and the imaginary part denoted by X. Now, different cases are named as follows. Okay. Are named as given below. Okay, let me provide this definition in a compact way, namely through a table. And this is how our table looks like. Okay, so this is the case when R, the real part, is 0, so that corresponds to the first row, and the second row is representing the case when R is positive. Note that R cannot be negative because we're considering a passive situation. As for the imaginary part, X, or the reactance, can have any sign. It can be 0, it can be negative, or it can be positive. And depending on those signs, we will now name the one port, or classify the one port as follows. So here we have the case where the average power is 0, okay, dissipated in the resistors in the circuit. Therefore, what we're dealing with is a purely capacitive case. Why capacitive? Because X, the imaginary part, negative, means that the total stored energies in the capacitors are larger than total stored energies in the average stored energies in inductors. Therefore, the capacitors are sort of dominating the overall one port. That's why this is called capacitive. This case is called capacitive. And the dual case is called purely inductive. Okay? For the purely capacitive or purely inductive case, the impedance is purely imaginary. As for our positive, if the imaginary part or the reactance is 0 for our impedance, then this is called a resistive case. Note that resistive case does not mean that we only have LTI resistors inside. Okay? We may have, for resistive case, still capacitors and inductors, and they are all storing energies. They are not just laying around doing nothing. But the stored energies in the inductors equal the stored energies in the capacitors, so the difference is 0. Therefore, the impedance will not have an imaginary part. It will have a 0 imaginary part. Okay, so that case is called resistive. And if X is negative, again we have the capacitive case. This time it's not purely capacitive, it's just capacitive. And finally, this case is called inductive. Okay. And these two cases together, when R equals 0, sometimes called the purely reactive case. Okay. And this is R0, X0. That means Z0. Well, it doesn't have a name. If you want a name, you can call it the short circuit. Okay. Okay, so let's apply this definition to an example before we finish this lecture. Okay, so this is our one port that contains 3 components: a resistor, a capacitor, and an inductor. 1/16 Henry, 1/3 farads, and this is 0.5 ohms. Okay, now the question is, given this one port, is it resistive, capacitive, inductive, or purely capacitive or purely inductive? Now, that's a premature question because this definition is based on impedance. Okay, and impedance depends on the frequency of oscillations. Hence, whether this guy is resistive, capacitive, inductive, or anything from this table depends on the operating frequency. Okay, so the answer will depend on frequency. So let's therefore obtain the impedance for this one port, and to do that we convert that to phasor domain first. So here we have inductor, and here we have our capacitor and our resistor. J omega L is the impedance of the inductor, so we have J omega over 16 ohm. This is 1/J omega C as the impedance, hence we have minus J3 over omega ohms for the impedance of the capacitor. And as for the resistance, well, it's independent of the frequencies. The impedance of the resistor always equals resistance, 1/2 ohm. And let's compute the input impedance, Z. Z equals this impedance plus these two impedances connected in parallel. So we have J omega over 16 plus the sum of conductances. Then we take the inverse, and the conductance for the resistor is 2 mhos, or 1/1/2. And as for the capacitor, it's what? J omega over 3. That's the J omega over 3. That's the conductance. Or 1/J3 over omega. Okay, so So that's 1 over impedance, which is admittance. Okay, and that yields, after simplification, j omega over 16 plus 18 minus j 3 omega 36 plus omega square, and that can be written as the following single fraction: 288 plus j omega square minus 12 over omega square plus 36. Okay. And then, since the denominator is always a positive real number, we can determine the sign of the real and imaginary parts by just looking at the term in the numerator. And then, by applying our definition, we reach the following conclusion. Hence, Z, our one port, is resistive okay, for such and such frequencies, inductive for such and such frequencies, and capacitive for such and such frequencies. Now let's figure out the blank pieces in our definition. So resistive means, one-port resistive means, remember our definition, remember the table, it means that the imaginary part is 0. Now we'll look at the imaginary part of Z, which is which we can do by just checking the numerator term. So this is the imaginary part, omega times omega squared 12. It's 0 when omega equals 0 or omega squared equals 12. Okay, so when either omega equals 0 or omega equals square root of 12 radians per second, we have no imaginary part. The impedance is purely real, therefore the one port is said to be resistive. Okay. Now, when omega square is larger than 12, then this is positive, the imaginary part is positive, and our one port therefore is inductive. Okay. For omega larger than square root of 12 radians per second. And for the remaining omegas, we have the capacitive one port. Okay, in other words, for omega between 0 and 2 times square root of 3, our one port is capacitive. Okay, radians per second.